Now let's take a design change problem. We have a 360 view ECU module that's being overheated. So in automotive industry, in a certain company, we have a vehicle that one of the features in that vehicle having 360 view of the vehicle. If you're familiar with the kind of satellite view of the vehicle that you can see while reversing or while moving in a tight area, you can see what's around you. It's basically a group of cameras around the vehicle that they stitch together and collaborate through an ECU module to give you kind of top view, a kind of fake top view of the vehicle, but still useful in driving. That exact module was located in a certain point in the vehicle, and that caused the ECU module to overheat, and that ran some problems to the supplier who supplied that ECU module to the vehicle. So how do you start? So the module in the past was located under the driver's seat, somewhere here. And if we imagine, of course, the driver's seat is here. The ECU was here with no problems. Then the company decided to go with a new design, and ended up the customer, which is the kind of specific vehicle manufacturer, decided to move the module for kind of packaging constraints. So they said, okay, we can put this module probably with other modules that we put somewhere under the instrument cluster. If you can imagine, this is the steering wheel. You know, where's the driver knees? Somewhere here. So we have a couple, not only one module, we have a group of modules been located over there based on the customer requirement. So the supplier have not much choice but to put his module there. Okay, well, the module is overheating. That's the initial testing for the module. It's saying the module is overheating and expected to keep overheating as long as it's in that location. Why? So that's kind of the way you do the thinking in order to decide how your product is going to run in that specific environment. So sometimes you have a lot of constraints you want to keep in mind. So in this case, let's go to the right drawing in here. So this is the module we're talking about, the ECU module. It's been overheated. Just right to the left of that module, 14 millimeters away, there's the wipers ECU of that vehicle, and on the right 5 millimeters away there's the smart key ECU. So two ECUs that are generating heat are right beside that ECU module, and I can say that's not a good engineering location for that module, especially if that module based on the requirements and properties, if it's producing a lot of heat, if there's no internal cooling, like if there's no active cooling like a fan in that module, then there is a problem. And most of these modules, by the way, in automotive industry, they are fanless, just to avoid any kind of unnecessary noise to the customer or to the driver who gonna buy that vehicle, and so on. So that's a problem. That's a change point. That change brings a lot of problems. So you change the module architecture and you change the module location based on a certain constraints from the customer, and that's caused overheating. In the future, we take this example again after we learn more about all the details of DRBFM, and we will tell how we're gonna dig down into that problem. But I'm just trying to lay down here how's the mindset, you know, like when you move from A to B, problems show up. How are you gonna avoid problems? You can think, I can tell you some hints right now. So you want to think, okay, this module, if I need to think, can I move it out of there and go somewhere better ventilated, and away from other heating elements, or I have no choice with that? Secondly, how I can make the module passively dissipating the heat in a more efficient way, and so on. So those are the details you want to look at when you're talking about the change with the DRBFM mentality. If you go to the next example, there's a dimmer switch for a certain vehicle manufacturer that's been melted and been degraded pretty fast. Like, you know, each switch have a certain lifetime based on the manufacturer. If all the customers that are using that vehicle, they're complaining that, hey, this dimmer switch is going bad very fast. So you want to look back in that problem and try to drive a change. In this case, you are doing a positive change. So you want to go from a switch that can't handle and understand why he can't handle and he can't pass the durability as intended and the lifetime expected life, and go from there. So if you look at the switch details right here, so you can see this is how the contact mechanism is happening. That's one thing. Second thing, if you look at the back, you go back to your drawings and look at the drawings. How was the mating between that switch and the surrounding surfaces? So this is the switch and these are the surrounding surfaces, and you can see when you are applying force on that switch to click and unclick, that will cause some kind of interference between the edge of the mating surface and the edges of the main switch. So that will make the switch lose the durability fast. Secondly, if you take a closer look in terms of testing and look under the microscope on the surface, how does the surface do? Is there any debris? Is there any wear? Is there any unneeded grease, carbon deposits? You know, there's many things to test in terms of engineering to tell what kind of failure mode you're having. So you come out with a conclusion and you change that problem, avoiding all the things that you noticed and using the lessons learned, and you move forward and hopefully the problem will be solved. So if we want to see how does the DRBFM happen in main kind of milestones. So firstly, you have a big system, a lot of assemblies, sub-assemblies and parts. So firstly, you want to focus part at a time or system at a time. So first you choose DRBFM part selection. You choose your part. Then of course, assuming that everybody involved already had DRBFM training, similar as what you are having right now. So you are capable of doing the mindset and philosophy of DRBFM and thinking through that lens of DRBFM. Then you do kind of an A, B, or S rank development. So you can say this change is rank A, rank B, rank C. It's mainly saying this is a change with a high possibility of failure, low possibility of failure, and that kind of mindset. Then you do the technical review, as we said, design review, sitting with the experts and getting their inputs. So you have inputs and inspections and eventually reflection. You reflect what you learned and the suggestions you received on your product or on your specific part, and you repeat with other parts. So the process repeats as a cycle with other parts until you cover all assemblies, all parts involved, to be able to deliver an overall high durability, high quality assembly or part or product. Eventually, DRBFM procedure overview. If you want to put the DRBFM procedure in 2 milestones, we have the pre-work that's done by design engineers and planners. Then we have the department discussions. For the pre-work of design engineers, so firstly, the engineers need to visualize the system clearly. Assemblies, sub-assemblies, parts, and give numbers, give letters, give the ability to whoever come after you to call out that part. Oh, part number A in assembly 1, 2, 3, blah blah blah. So you can identify that part and take it on the side and write details about it and discuss it. Then you break down the system hierarchy, showing related parts. As we said again, assemblies, sub-assemblies, and parts. Then you detail the changes. Why did you go from switch A to switch B? And what happened exactly? What did you change? You change dimensions, you change material, you change location, and so. Then you define the functions or requirements. What does the switch do? What does the mating surface do? What does the spring inside the switch do? And why did you change the spring? Did you change the length? Did you change dimensions? Did you change any engineering properties of that part or sub-components inside of it? Then you identify the concern points due to change. So you create a matrix, and that matrix having change points crossed with functions. How does these interfere with each other? Is there any flags raised? Is there any alarms or any identified parts that needs to be discussed in details? Then you dig deep more to find root cause. Why do you think this is a suspect part? Why do you think this thing will fail? And so on. Then you clarify the effects to the customer. If anything affecting the customer, like if you're delivering an ECU to a company who deliver vehicles and pickup trucks, how does that affect the customer if the ECU overheat? Okay, that will make you guys lose a feature. Maybe you will have warranty vehicles come back to your dealers and so and you will lose this much and you could run into these problems. So we gotta solve it early. Then you explain the design steps taken to prevent that concern. So if that concern stayed, this is what will happen, but these are the steps we took and we think it will take care of the problem. Then secondly, you go with department discussion. You discuss, are there any other concerns that we didn't cover? Is there any considerations, other considerations for the cause that we didn't take in mind? Then you discuss if the concern can be resolved through design steps before we have anything physical, and if there's any steps that can be taken to prevent the concern at first. Then you discuss and determine the recommended actions. Like after all those processes, if there's any leftover problems, what are recommended actions moving forward and reducing the risk?